Welcome, listeners. So, here we have again gathered for the third part of our discussion on metamorphic rocks, and this is in the broad topic of our discussions on fundamentals of geology. So, here, after looking at the processes of formation of metamorphic rock and also discussing about the various agents that are controlling the processes that are involved for the formation of a metamorphic rock. Followed by that, we have also discussed about the concept of grade and phases, that how it evolved, how from the concept of index mineral to define a particular grade of metamorphic rock to how we have reached the idea of mineral assemblage belonging to a particular metamorphic phases. And also we discussed about the various mineral assemblies that are stable in a particular pressure temperature domain over metamorphic phases. So, now after the broad discussion on the formation of metamorphic rock, metamorphic grade, metamorphic phases, we will now plunge into the discussion on the textures and structures exhibited by metamorphic rocks. So, obviously they are broadly, I can say that metamorphic rock, based on structure or texture, they can be grouped into two broad categories. One is the foliated type, the other one is the non-foliated type. So, as the name suggests, foliated type means the metamorphic rock which exhibits some kind of planar structures in it, like planes or layers exhibited by the rock. On the other hand, when we are talking about non-foliated rocks, it means it kind of look like homogeneous rock and that is devoid of any kind of planar structure or layering, like that of several igneous rocks. Like that, for example, if I take a sample of granite, then I can say that it looks homogeneous in nature. Similarly, in case of metamorphic rocks as well, if I am looking at metamorphic rocks, then you can either see some kind of layering or planes or planar structures that are present in the rock, or either you do not have any kind of planar structure that are present in that rock. So, broadly you can categorize these metamorphic rocks based on the presence of foliations and absence of foliation into foliated type and non-foliated type. So, there are several factors that affect the formation of several textures or structure in a metamorphic rock, and like as the processes of the metamorphic processes that are governed by changes in the pressure, temperature, chemically active fluid, like we have discussed. Similarly, these factors also contribute to the formation of several texture in a particular metamorphic rock. So, obviously, to start with the first one, which is essential always, that what is the composition of the rock. So, in that case, the first factor has to be the composition of the parent rock or the protolith. Like we discussed, that protolith is the parent material of any metamorphic rock. So, minerals of the parent rock or protolith determines the degree to which each metamorphic agent brings about the change. Each metamorphic agent means, again we are talking about the pressure, temperature or the chemically active fluid. Then again, the most important one is the temperature that is prevailing during the metamorphism of a rock. So, it is controlled primarily by external flow of heat to the rock, minerals that are stable over temperature range, and some new minerals which are strictly metamorphic in nature or has resulted or formed during in the formation of a metamorphic rock. So, the presence of new minerals also govern the texture and structure in a metamorphic rock. Then again, obviously the other agent, that is pressure. So, the pressure during metamorphism, it typically increases 1 kilobar per 3.3 kilometer of burial in the crust. There are exceptions to this as well, but this is, generally speaking, this is the standard. Generally proportional to the burial depth within the earth, like we discussed about the burial metamorphism as well. And minerals formed under high pressure have more compact structure and high density as well. Then you also have different tectonic forces that are involved in the in the formation of certain textures, and that is generally led by the factor of deviatoric stress or directed stress as well. So it depends that how structure will develop in a particular rock. It is also a function of the stress you can say incurred by that particular rock. Then obviously the role of chemically active fluid is very important, because they play a catalyzing role during your metamorphism, because whenever there is some injection of some chemically active fluid in the process of metamorphism, it will initiate certain kind of reactions due to the high amount of, you can say, and this chemically active fluid is mainly your hot water. So many reactions get initiated when this hot water comes into this metamorphic system. Then obviously, as it is the hot water we are talking about, so the rising temperature causes water release from the unstable minerals which were present in the protolith, and they might also form new minerals. On the other hand, sometimes the water molecules, they get combined with the existing minerals and they result into formation of new minerals. For example, if some chemically active fluid which is rich in water gets reacted with a pyroxene group of mineral, it might get modified or transformed into an amphibole group of minerals. So your hot water, like I said, are being very reactive, acts as rapid transport agent for mobile ions. And obviously the most important thing is the time, that how much time is required to complete a particular metamorphic process. So the formation of metamorphic minerals and texture may take thousands or millions of years as well. So longer time period of metamorphism allows the growth of larger minerals, distinct texture, and very well defined foliation, resulting into a foliated rock. Then obviously there are processes which are operating during the formation of a metamorphic texture. The first one is obviously recrystallization, because we have talked about that metamorphic is generally speaking, it is a solid to solid state transformation. So your crystallized or your minerals which have already crystallized should go into some kind of recrystallization to means you can say to form new minerals. Also, if I say, then it might result into formation or transformation of a parent mineral into its some other polymorph of its same composition. So your recrystallization changes shape and size of grains without changing their composition, because we are talking about that the composition will not change, but the structure of the mineral might change, resulting into transformation of the parent mineral into a different polymorph of the same composition. Then you can also relate with phase changes that transform one mineral to another with same composition but a different crystal structure. So this was I was also referring to along with the crystallization. Then there could be neocrystallization or some new metamorphic reaction that are now going on during the formation of the metamorphic rock, results in growth of new mineral crystal which were not present in the protolith earlier, that differ from those of the protolith. Chemical reactions digest minerals of protolith to produce new metamorphic minerals. Like I was saying, that if some chemically active fluid is present in the system, it will react with the parent minerals or the minerals that were present in the protolith. Now they will form new minerals in the newly formed metamorphic rock. Pressure solution processes takes place when a wet rock is squeezed more strongly in one direction, producing ions that migrate through water to precipitate it elsewhere. So if I just think of a rock, for example shell, and there are already some layers that are present in the shell, then I can compress it I can also take an example of a shell, and I can see that if it is obviously the protolith of this particular rock is or was a shell, now this has become a slate. So earlier there were also some layering, like the primary sedimentary layering, that were present in the shell, like we have also discussed in case of the sedimentary rocks. So there are some planar features that were already present in the shell. Now due to a directed stress perpendicular to these layers, it will finally or it will further compact this material into a very, you can say, hard compact, highly dense material, and resulting into the formation of this rock, that is slate, which is, you can say, a low grade metamorphic equivalent of shale. Then you can also induce plastic deformation when the rock is squeezed or sheared at elevated temperature and pressure, and under this condition minerals behave like plastic and shape change without breaking apart or without showing any, you can say, brittle kind of mechanism within it. So it will essentially be governed by plastic mechanisms. So again, classifying metamorphic texture broadly, there are 5 classes of metamorphic texture. The first one is your palimpsest texture, then you have typomorphic texture, then you have reaction texture, then corona texture, and also intergrowth textures. So we'll handle it one by one. So the first one, that is your palimpsest textures. These are primary texture of original rock that is somehow getting, you can say, saved from the processes of the metamorphic rock. That means your metamorphic rock will bear some signature of its original texture of the protolithic material. So in the occurrence of your palimpsest texture are mainly found in low grade metamorphic rock, where you don't have a very high means change in temperature or very high elevated temperature or pressure, but at about, for example, 200, maximum 250 degrees centigrade, max to max 300 degrees centigrade, your metamorphic changes are going on. But the primary textures that were present in the protolith, they are somehow being saved or they are resisting their complete destruction during this process. So there will be some remnants, I will say, there will be the remnants of the earlier signatures that were present in the protolith, also they will be present in the finally formed metamorphic rock. So these are also known as relict texture, relict of the protolith that is still preserved within the newly formed metamorphic rock. There are a few terms like blastic or blast that is used as suffix to represent the resembling metamorphic equivalents of igneous rock. So for example, if I take the first example, that is blasto-ophitic texture, we have discussed about ophitic texture earlier when we discussed about igneous texture, that when a plagioclase grain is surrounded or it is protruding a pyroxene grain, or it is completely surrounding by a pyroxene grain, in that case it is either ophitic or subophitic texture when it is obviously originated from an igneous process. Now if I see the same kind of texture in your metamorphic rock, in a newly formed metamorphic rock, then also if I am getting a similar texture, that there is this large pyroxene grain, you have your plagioclase that are present within this grain, but essentially it is a metamorphic rock. So then I will simply refer that texture as blasto-ophitic texture, not only ophitic, it is now blasto-ophitic texture. Then you can also have blasto-intergranular texture. Again, talking about intergranular texture, it is again an igneous texture. So your igneous relic texture in metamorphic rock that show occupancy of interstices found between plagioclase crystal by ferromagnesium minerals like pyroxene and olivine. So you can also relate it with the simple intergranular texture of your igneous rock, where you have this you can say sets of your plagioclase grains which are interlocked in an, you can say, in a triangular fashion, and the interstitial spaces are obviously filled up by some ground mass. So, in that case it will be intergranular, but if it is exhibited by a metamorphic rock, in that case it will be blasto intergranular texture, and these interstitial spaces will be now filled up by your ferromagnesium minerals. So, that is your blasto intergranular texture. That means again the blasto term is used as a prefix here, sometimes it is also used as a suffix. So, here it is used as a prefix. That blasto intergranular means it is definitely a relic texture or the relict of the intergranular texture that was present in the igneous protolith. Now, it is also present in the newly formed metamorphic rock. So, that is why I will categorize it under blasto intergranular texture. Then you also have blasto-porphyritic texture, simple like that of the normal porphyritic texture exhibited by, for example, basalt, that you have large grains of your plagioclase that are sitting in a very fine grained ground mass. So, that is your porphyritic texture. We have discussed about that in our discussion with igneous texture. So, your larger grains of crystal that are surrounded by fine grained matrix or glassy ground mass as well will be obviously your porphyritic texture, but when it is exhibited by a metamorphic rock, it becomes blasto-porphyritic texture. Then you also have cumulate texture, that early formed crystal with high density settle down, giving rise to cumulate texture. Again, if this kind of texture is exhibited by a metamorphic rock, it simply becomes blasto-cumulate texture. So, you can see that how this word blasto is being used as a prefix to name the relic texture that is exhibited by a metamorphic rock. The relic texture from where? The relic from the initial protolith, which could be an igneous rock, sometimes it could be a sedimentary rock as well. So, the newly formed metamorphic rock will bear signatures in low grade metamorphic processes. It will finally result or it will bear the signature or textures that were a characteristic feature of a particular igneous rock will be preserved in the metamorphic rock as well. Then you have typomorphic textures, and they are characteristically developed in metamorphic rock either by dynamic forces or by thermal influence, like we discussed about dynamothermal metamorphism, where your both pressure and temperature play a role in the formation of a particular metamorphic rock. So, based on that also, whenever we are saying dynamothermal, then you can just by the terminology we can say there is a strong influence of the dynamic forces or the tectonic forces that are governing in the formation of a specific set of texture or structure in a metamorphic rock. So, if there are several texture in response to the formation of dynamothermal metamorphic rocks, and obviously they are the best example we can think of is of your shear zones that are, we will be also discussing shear zone in our subsequent lectures in a little detail, not at very advanced level, but in a little detail. But in that case also you can think of a simply a zone where your, for example, two wall rocks has passed or is moving past one another, and in between this zone you will get obviously due to some tectonic forces the wall rocks are moving past one another, and also due to this movement some frictional heat is getting generated. So, in that zone which we generally refer to as the shear zone, you will get some rock which will exhibit textures like porphyroclastic texture and also myelonitic texture. So, your porphyroclastic texture like this one, that you will have some clast like this that is surrounded by some ground mass, but this clast will be more resistant or rigid in nature in comparison to the surrounding ground mass. So, due to deformation, softer materials get crushed and form ground mass, while resistant minerals get fragmented and appear to be larger than the surrounding minerals. So, here you will get two distinct grain size distribution of the same mineral or the coarser grained porphyroclast and finer grained fragments are also present. Larger grains are referred to as the porphyroclast, and so the texture is referred to as a porphyroclastic. Remember, this is not blastoporphyritic, this is porphyroclastic, where you have strictly a you can get confused that whether it is the same kind of grain size distribution like we see in case of your blastoporphyritic, where you have again two broad classes of your grain size, but in case of your porphyroclast it could be of the same mineral in composition, that some, for example, if I am looking at myelonitic quartzite, in that case what will happen, that there could be some large quartz grains which will somehow escape the recrystallization process, but the rest of the ground mass that are surrounding it will go into your recrystallization, changing its shape and size. That means it will be more fine grained, the ground mass will become fine grained, but you will have some relict or remnant clast which will escape this deformation and it will be more rigid in comparison to the rest of the quartz grains that are present. So, the resulting texture will be a porphyroclastic texture, not a blastoporphyritic one. Then you can also think of myelonitic texture, which is very characteristic of shear zone rocks. So, the development of foliation planes now or oriented minerals in metamorphic rocks, in particular orientation of minerals. So, based on that they are segregated as protomyelonite, then a normal myelonite and also ultramyelonite. So, you can see here there is a series of your myelonitic texture. Here you will not be very confident of any foliation or any layering, but in the next photograph that is marked as B, you will see that there is some kind of layering is now present, or some kind of distinction you can also make if you go from the left side of the photomicrograph to the right side. Then in this case you can see there are some in both these cases C and D, there are ground masses which have recrystallized and is giving you very fine grain size, but there are also some remnant class that are present which have escaped this process of recrystallization, be it of a different mineral, sometimes it could be having the same mineral composition. Then if I increase the intensity further, then what becomes is your ultramyelonite, where you can see there is complete destruction or reduction of grain size. There are no large clasts are preserved here. So, you have a very well defined planar fabric or lines you can see on this particular section. So, these lines are defining your planar fabric that are present in this particular metamorphic rocks. So, in this case this will be your ultramyelonite or ultramyelonitic texture. So, you can say it is a matter of the percentage of the matrix minerals. If it is very less, then it will be considered as your protomyelonite. If the matrix material increases between, for example, 50 to 90% of the whole volume of the rock, then it becomes myelonite. If even it exceeds more, if the ground mass or the recrystallized matrix material here becomes dominant and it has a very penetrative and very strict layering, you can say, in that case it will be considered under ultramyelonite, which will have a matrix percentage of more than 90%. Then the other typomorphic texture that are formed due to thermal effect solely, you can say the first one is your nodular texture, your growth of oval shaped porphyroblast. Now, porphyroblast and clast, there is a difference, that porphyroclast are definitely the relict of some earlier existing grain, but if it is a porphyroblast, obviously porphyroclast and blast, they both mean larger grain in comparison to the rest of the ground mass. So, they refer to larger or coarser grains, but if it is strictly a new mineral that is being formed during the process of the metamorphism, it will be considered as porphyroblast. But if it is having some character, or some you can say the relict grains from its earlier protolith, in that case it will be considered as porphyroclast. So, growth of oval shaped porphyroblast, and you think blast means, again it is strictly of metamorphic origin, it has no relation with your means protolith lith of that particular metamorphic rock. So, your oval shaped porphyroblast of minerals like cordierite or scapolite in association with quartz and other minerals like this. Then you have also granoblastic texture. So, it is very characteristic texture of now non-foliated rock. We have discussed about foliated and non-foliated. So, your granoblastic texture, they are typically present in non-foliated metamorphic rocks, where your grains are equigranular to nearly equigranular. Grains form a very welded mosaic of recrystallized mineral grains like this. You can see this one, a very mosaic, there is no, you can say, spaces in between the grains. So, this is an example of a monomineralic quartzite, where your quartz grains are forming this kind of polygonal boundaries and very well defined T and Y grain boundaries or junctions between the grain. And so, if it is a polymineralic, it can also form a polygonal granoblastic texture. So, it varies from equidimensional with straight boundaries to irregular boundaries to anhedral boundaries, which are referred to as interlobate granoblastic or amoeboid granoblastic, like the amoeba shape. When mineral grains get interlocked, randomly oriented and prismatic or elongated with common triple junction, it is called decussate granoblastic texture, this one. Okay. So, the other type of typomorphic texture is solely based on the crystallization, that the textures formed during the crystallization process. So, the first one is again your porphyroblastic texture, like I was referring to. It is same as that of, you can say, if it is porphyritic, it is obviously of igneous origin. When we are saying porphyroblastic, that means it is typically of metamorphic origin. Still you will get these two classes of grain size distribution. One, there will be larger grains, obviously they will be surrounded by finer grains in the ground mass. So, you have the coarse grain mineral occur in the fine grain ground mass. So, the individual large coarse grains will be termed now as porphyroblast. And like I mentioned, it is extremely similar to that of the porphyritic texture exhibited by your igneous rock, for example basalt. But in this case, porphyroblastic means it is strictly a metamorphic texture, because you have that word blast here. Again you have poikiloblastic texture, again it is same as that of the poikilitic texture we discussed in case of igneous rock again, but here again you have that word blast though. So, that means again it is strictly a metamorphic texture. So, if you can say there are marked with addition of several fine grain inclusion within the porphyroblast. Orientation of the mineral grains as inclusion may be random, hellitic or spiral depending on its mode of occurrence, that how your coarse grain, that is porphyroblast, has rotated or has, you can say, displaced from its original position, or has rotated at its position during the formation of the metamorphic rock. You can also think about reaction texture, like we discussed again in case of your igneous rock, but in case of metamorphic rock, when we are saying about reaction texture, that means there is some role of the chemically active fluid in this process. So, new mineral formed by replacement of older mineral, or by reaction between two phases, or sequential reactions. So, this reaction will be initiated by the injection of the chemically active fluid. So, now there are various kind as well, just to refer to two of them, two common reaction texture. The first one is reaction rim texture, where you will get replacement of older phase takes place along rim of the mineral. Rim of new mineral forms around core of older mineral like this. Rim becomes irregular and forms contact between two mineral phases, and rim indicates some reaction in taking place between the both phases. So, there is continuous ion exchange between the rim and the core of the reaction rim texture. Then you have the caliphytic texture, where replacement takes place, but by intergrowth of two or more minerals, New minerals completely encircle the replaced mineral, and it is also referred to as a replacement texture. So, here you can see the presence of garnet, then you can also see the presence of your clinopyroxene. So, in this replacement texture, in between you have some other minerals like chlorite, which is retaining the shape of the garnet, but has now transformed into a new metamorphic mineral which was not present earlier in the protolith. So, definitely it is a replacement. So, it is a newly formed metamorphic mineral which was not a characteristic of the original igneous protolith. And then you can also think of the corona texture that may develop in a retrograde as well as prograde phase of metamorphism. Retrograde means when your temperature pressure are falling, prograde means when your temperature pressure are increasing. So, one or more minerals form complete rim around older phase in center of the core like this one. So, its geometry resembles like a corona, and corona can also form in igneous processes as well. So, rim layers formed may change from 1 to 5 in number depending upon number of reaction that has taken place between the minerals. So, there could be one more than obviously one. So, there could be 2, there could be 5 minerals that are present in that, and you also have some intergrowth texture that are exhibited similar to that of again your igneous rock. Some intergrowth texture can be also or can also develop through your metamorphic processes. So, the again to discuss the two commonly commonly occurring your intergrowth texture, the first one is your symplectite texture that gives you a worm like appearance of minerals formed along the boundary of older minerals. You can look at this photomicrograph. Fine grained minerals intergrow irregularly due to some reaction at the rim of previously formed minerals. So, you can see this from this photomicrograph where your OPX grains are forming here, means orthopyroxene grains are forming here along the margin of your garnet, and you have potash feldspar and cordierite surrounding it. Then you can also have myrmecite texture, which is again earlier people used to think that myrmecite texture is only possible in case of igneous rocks, but myrmecite texture can also form in case of metamorphic rock. So, it is also an example of your symplectite texture. Vermicular or wormy quartz intergrows within the plagioclase just like that of your igneous rock, but myrmecite can also form in case of metamorphic rock. There are myrmecite which have or which can form due to certain changes in the directed pressure as well, means that is related to some kind of, you can say, deformation. We will talk about deformation later on, but you can also think about that some kind of pressure or directed stress is also governing the formation of the intergrowth texture, but it is commonly seen in high grade metamorphic rocks. We can again refer to high grade means we are going above a temperature of 600 or 700 degrees centigrade. So, in that case you can get this kind of myrmecite texture. So, and apart from that, like I was saying in the beginning, that you can think of foliated metamorphic rock, you can think of unfoliated or non-foliated metamorphic rock. Foliation in metamorphic rock are also sometimes combined with lineations. So, there could be planes, there could be lines resting on the plane as well. So, based on that, again the foliation indicates a texture displayed by metamorphic rock that exhibit a preferred directional orientation, alignment of platy or flaky minerals, and that will be exhibited as your layering or foliation that is present. So, if I simply look at this rock, this cystosity can be seen. It is a specific type of foliation which is referred to as cystosity, like we discussed when we discussed about metamorphic grade, that as you increase the grade from shale to the first metamorphic rock slate, then you will have phyllite which will also have some foliation. Here the next grade one is your schist, which will have very well defined foliation and layering in the rock. So, you can see just by, and if I simply try to separate the layers, because your muscovite and biotite minerals are present in it which are platy and flaky in nature, they are getting separated from the surface of the cystosity or from the side where your you can say the means you can see the foliation plane from the side. You can also separate the grains, individual mineral grains like this, or a set of grains from that surface of the rock. So you can also have foliation and lineation that are exhibited by majority of the metamorphic rock. But if a metamorphic rock is of very high grade, for example granulite facies, in that case, and after that it will finally go into partial melting, but within the granulate facies rock, you can say the structure is more or less homogeneous. You will not get very well defined foliation or no lineation it. So there are other planar features like slaty cleavage, like we have just seen here in the earlier example of the rock, that is slate, which is a low grade metamorphic equivalent of shale, that is a sedimentary rock. So here you can see some cleavages or some again foliation planes that are your slaty cleavage. Here this one I was referring to as your cystosity or your cystose structure. And you also can have, for example, gneiss like that. When the grade is little bit higher, then you can't really separate the layers simply with your nail or your hand, but you will be able to see this layering always in case of a gneissic rock. So again it's a matter of grade, that how this slate is getting transformed into a phyllite like this. I'll show you here. So this is a phyllite again. So the slate will be with higher grade of metamorphism, it will get transformed into phyllite. Then you also have, after phyllite you have this cyst that is exhibited by this very well defined cystosity, and the final high grade one is your gneissosity like this, where you can't really separate the layers, but you can have an idea that there is certain banding that is present in the layers. And the last, a few other metamorphic textures like some cataclysmic texture and some pseudotachylite rock might also develop in response strictly to your dynamothermal metamorphism that goes on in the shear zones. So these are very, you can say, typical texture that you can only get in case of your shear zone rocks. So here I would like to conclude our discussion on metamorphic texture. Thank you.